You got it. Okay. So this is the last recitation, thank God. But I'm starting all over the summer, so from chapter 1 again. But this is a pressure vessel problem, and I'm just going to derive longitudinal hoop stress so you guys know where it comes from. Because some of you guys didn't know where it came from, so I want to show you. All right. So we want to draw a free body diagram, cutting it in the ZX plane. That will give us a hoop stress. So let's draw a free body diagram, cutting it in the ZX plane. Okay, so when we cut in the ZX plane, obviously we're going to have stresses in this wall. They're going to be pointing upwards in the y direction. And this is a hoop stress. So this is sigma h, sigma h. And they give you dimensions over here. They give you dimensions. They give you the length of the cylinder, they give you the thickness of the wall, and they give you the radius, the inner radius. And inside here is fluid with pressure P. Okay, so there's going to be a pressure and it's being facing downwards. So there's a pressure acting downwards. So I'll call this P, and then you have hoop stress along the wall thickness over here, pointing up in the y direction. This is in the negative y direction, P. Okay, so these are the only forces, right? They're stresses, but they're forces because they act over an area. So they give you this thickness, the inner radius R, and they give you the wall thickness. This wall thickness over here is T. Okay, and this length over here is L. Okay, so we're going to have to do a force balance, right? It's a simple force balance. The forces are only acting in the y direction. So let's sum the forces in the y direction to be 0, taking upwards to be positive. All right, so P's acting over this area over here, right? So P is facing downwards, so it's minus P times its corresponding area. What's its area? It's L times 2R, right? L times 2R is the area of this rectangle over here. You guys see that? So it's 2R, right? That's this distance, times L is this distance. That's the area, right? And sigma h is pointing upwards, and it's acting over two areas. There's a rectangle here, and there's a rectangle here, right? So you have plus sigma h times this corresponding area, which is just L times T, plus sigma h times L times T. Okay, all right, so that's your force balance, right? So you can move the, you could move this term to the right. You have 2 sigma h times LT, right? That's what this term is equal to P 2RL, right? And we want to solve for sigma h, so you divide by 2LT. So sigma h is equal to P 2RL over 2LT, right? And what does that reduce to? Sigma h is equal to what?
PR over T.
PR over T. Okay. All right. So now we want to derive the longitudinal stress. Okay. So we're going to have to do a cut in the XY plane. So this is for the hoop stress. And I guess I'm just going to use this picture.
Shh, give the message.
Okay, so now we're going to cut in the XY plane. Okay, so cutting it here. Let's just say we cut it somewhere over here, but I'm just going to use this base to make it more convenient so I don't have to redraw it. Okay, so there's stress all along this area. This is sigma L. So it's acting along this face. Right? And then there's a pressure in the center. So this is P. Okay? And P is acting all along this area. Okay? So, can you guys see this? The wall thickness is T, and from the center of the circle to the inner wall is R. Okay? So we have to do another force balance. So if this is a Z direction, we'll sum the forces along the Z direction to be 0, taking this direction to be positive, because outwards was positive, okay? So sigma L is in the positive Z direction. So sigma L times its corresponding area. Well, its corresponding area is 2 pi R, which is this dashed line, times the wall thickness. That's the area. 2 pi R, that's the circumference, that's this dashed line, times the thickness will give you the area. Okay, so that's positive, and pointing into the board is P, so that's minus P times its corresponding area. Well, you can just see that's pi R squared. That's the area of this dashed line, this whole area here. So this is pi R squared is equal to 0. So you can solve for sigma L. Move this over, so you get P R over 2P as your final solution. So this is a hoop stress, the longitudinal stress. That's where it comes from. Okay? And I don't know if he showed you hoop and longitudinal stress for spherical pressure vessels. Did he show you that?
Yeah.
Oh, he did show you? Did he derive it?
Deriving, I don't know, but I remember we did do that.
Alright, I'll just derive it.
Disney goes, just sitting
Okay. Okay, so this is a sphere. I really can't draw a sphere. I don't know how to draw it. Whatever, that's a sphere. Okay. Okay, so it has. This also has an inner wall. It has a radius R and wall thickness T, just like the other problem. Okay, and there's fluid inside here with pressure P, right? So we want to derive the longitudinal and hoop stress, right? So we're going to have to cut it. If we want the hoop stress, we'll cut it again in the ZX plane. So we'll draw a free body diagram of that. Free body diagram of ZX. So we're cutting it in the ZX plane. So we have a picture like this. Okay. The inner radius is R, the wall thickness is T. Right, so there's fluid inside here. So there's going to be pressure pointing downwards, so this is P. And then there's going to be the hoop stress, which is pointing upwards, all along the cylinder, and the sphere.
What is this? Is this like a top view or something?
Yeah, I'm cutting it basically along this plane. Yeah, you could think of it as a top view. It's actually the bottom view. Okay. All right. So this is sigma H. But if you notice, if you cut it along the XY plane, you're gonna have the same picture, except this is gonna be rotated like this, 90 degrees. You guys agree? So sigma L would be equal to sigma H, right? So because if you tilt this 90 degrees, this is gonna turn into sigma L, but it's the same picture. You guys follow? Yeah. Okay. All right. So let's do force balance. Summing the forces in the y direction to be 0, taking upwards to be positive. What do you guys got? Minus P times what's the area?
Pi R squared.
Pi R squared plus sigma h times its corresponding area.
2 pi r times t.
Yeah, 2 pi r times t, okay, is equal to 0. So, in conclusion, you get sigma h is equal to p r over 2t. And that's also equal to sigma L, the longitudinal stress. Okay, so that's your formula for the pressure vessels. That's where it comes from. That was pretty easy. Any questions? Alright, so let's do chapter 9 problems and let's call it a day. Chapter 9 problems are really long. Alright, so on the test, on your final exam, you're definitely going to get a chapter 9 problem. It's either going to be statically determinate or statically indeterminate. So it's either one or the other. That's what you guys are going to get tested on. I picked this problem because I thought it was a good problem, because a lot of you guys asked me, how do you find W of x if you have a triangle, the triangular distributed loads, so I did this problem. Okay, so they give you the maximum load W naught, and they give you the coordinates where they start the beam. This is y, and this is the x direction. And they give you this length as L. Okay, so in this problem, they're asking for 3 things. They want the equation for the elastic curve. That's part A. Part B is the deflection at the free end, and part C is the slope at the free end. All right, in order to find B and C, you have to find A first. Okay. So we have to, obviously we're going to have to use calculus in this problem when we break up the distributed load. When we cut the beam into a distance x. So first, always with beam problems, you want to find the reactions at the wall. Okay, so this is A and this is B. So first, let's find the reaction at the wall. So before we even draw the free body diagram, we want to know how W depends on x, right? So we want to find W of x. How are we going to find that? What's the equation of the line? It's equal to mx plus b, right? Okay, so now we need conditions, right? So what's the condition at x equals 0? What does W equal?
0.
0, exactly. So W of 0, this is when x equals 0. I don't have to write that, I think you guys know that. So W sub 0 is equal to 0, right? This is condition 1. It's a boundary condition. What about the second condition? You guys know? Without looking at my notes. Well, the only thing they give you is W naught, the maximum load.
So W at L?
Yeah. At x equals L, W equals W sub 0. So this is the second condition, right? So with these two conditions, we can find the slope of the line. So with this condition, what is this going to give you when you plug it into the equation of the line?
B equals 0.
Yeah, B is equal to 0, right? Because you have 0 is equal to M times 0 plus B. So B is equal to 0, right? So there's no B term. And we would expect that, okay? So what about this this one? Oh, sorry, this one. The second condition. What is that going to give you? All right, so let's plug it in. We have W naught is equal to M, and X in this case is L, and B is 0. So we want to solve for the slope, so it's W naught over L, right? So we have the equation of the line now. W of X is equal to W sub 0 over L times X. All right, so this is the equation of the line for the distributed load. So we're going to go ahead and erase this, and we have W of X is equal to W naught over Lx. Alright, so that's the first part of the problem. Now we can solve for the reactions. And then we could cut the beam at a distance x and then solve for the elastic curve and everything, all that good stuff. All right, any questions on this? This is just algebra, math 101. Okay, so let's draw a free body diagram of this beam. Okay, so I'm drawing a free body diagram of the whole beam, right? You have this distributed load. Okay, so you have this distributed load. Okay, so this is W of x is equal to W naught over L x, right? This distance is L, the length of the beam. And what reactions do we have at the wall?
RA.
Yeah, we have a reaction force. So you guys want to call it RA. Okay, so RA. And what about, we also have a moment, right? Okay, so we have a moment. And it's going counterclockwise. You guys agree? Because this beam's going to try to go rotate clockwise. So this has to oppose it. So this is counterclockwise. So this is MA. Okay, so those are your reactions at the wall. Notice there's no horizontal force because there's no force on this beam anywhere that's going in the horizontal direction. So if you drew if you call this RAY and RAX, you'll notice RAX is 0. So I didn't even bother drawing it. Alright, so let's find those reactions. Let's find the moment at A and the reaction R at A. So let's sum the forces in the y direction to get RA. Taking upwards to be positive. What do you guys got? RA is obviously upwards, so this is RA minus, what do you guys got? This is where the calculus comes in.
Is it the integral of omega?
Yeah, it's the integral from 0 to L of Wx. So Wx is W sub 0 over L x dx is equal to 0. Okay, so this is the force balance in the y direction. We have no other forces. So we want to solve for the reaction. So RA is equal to W naught over L times the integral from 0 to L. This is just a constant, okay? So that comes out of the integral, and I'm moving this to the other side. So you have x dx, okay? So you can integrate that. So RA is equal to W naught over L times x squared over 2. And this goes from 0 to L. So you plug in the values. So you get RA is equal to W naught over L multiplied by over 2L multiplied by L squared minus 0 squared. So this comes out to RA is equal to W naught L over 2. Right? You guys agree? Okay, so we got the reaction at A. Now we want to get the moment. So let's do a moment balance at point A. Let me erase this now. Okay. Let's sum the moments at A. Taking counterclockwise to be positive. So we have MA because that's going counterclockwise. And then we have minus the integral from 0 to L. What do we have? A moment is x times W of x. So it's x times W naught over L x dx is equal to 0. So MA is equal to the integral. Remember, W naught over L is a constant, so that comes out. And you have x squared. It goes from 0 to L dx. So MA is equal to W naught over L x cubed over 3, evaluated from 0 to L. So MA is equal to W naught over 3L multiplied by L cubed minus 0 cubed. Alright, so the L's cancel, so you get W naught L squared over 3. Okay. All right, so we have the reactions at the wall. So this is equal to W naught L squared over 3, and RA was equal to what? It was W naught
L over 2.
L over 2. Okay? Alright, so we got the reactions now, and now we want to find the elastic curve. You guys learned the differential equation, right? It's a second order differential equation. It's d squared y over dx squared is equal to m of x over e I. This is to find the elastic curve. Okay, so you're gonna have to use this in part A. So we have to find the moment how it varies at a distance x, because we need this term, right? This term over here. So we're gonna have to cut the beam at a distance x. So let's do that. Alright, so let's draw the free body diagram from 0 is less than x is less than L. Okay, so the moment was W naught L squared over 3, and the reaction here was W naught L over 2, and this distance now is x, because we're cutting it at a distance x. X is varying from 0 to L. And what else do we have? So this is W sub x is equal to W naught over Lx. So what forces are we going to have at the cut? What type of reactions?
Here I have a shear and another moment.
A shear and a moment, yeah. Alright, so we have V and M, right? And these depend on X, right? Okay, so I'm going to call this, in this section, I'm going to call this V sub X. Oh, let me change it. Okay, so this is V sub X, and this is M sub X, right? Because they're going to vary with a distance X, with this distributed load. Okay, so we want to find these two, right? We're really after this, because once we find this, we could find the elastic curve.
Isn't the moment supposed to go the other way?
Yeah, but it doesn't matter. When you sum the moments, you're gonna get a negative. Like, it's okay. Just this is a standard direction. All right, so let's do a force balance first to get Vx. Summing the forces in the y direction to be 0, taking upwards to be positive. So you have W naught L over 2, right? What else do you have? Minus Vx. And you also have the integral from 0 to x. So it's minus the integral from 0 to x of W naught over Lx dx is equal to 0. Right, those are the only forces. 1, 2, 3. Okay? So we want to solve for V sub x. Vx is equal to, just move this to the other side, so you have W naught L over 2 minus W naught x squared over 2 divided by L, evaluated from 0 to x. Right? So this integral is just W naught x squared over 2, W naught x squared over 2L. So Vx is equal to minus W naught x squared over 2L plus W naught L over 2. Okay? Alright, we don't really need this, but I'm just showing you this anyways. Alright. Actually, you don't need it. I lied. You don't need it. Okay? Because you could sum the moments over here if you want. If you don't want to I always sum the moments over here in the next part, so that's why you need Vx. But if you wanted to sum the moments over here, you wouldn't need Vx. Okay. Can I erase this? Alright, so let's sum the moments at A. So we have W naught L squared over 3, that's positive, and then you have X times Vx, that's going in the that's going clockwise, so it's minus. So it's Vx. Oh, this is definitely gonna confuse you guys. Oh, you know what? Let's just call it V instead of V. It depends on X, but let's just call it V, because I don't want you guys to think I'm multiplying, because I'm gonna multiply by X, so it'll look weird. All right, so let's just call this V. Maybe that's why the book does it that way. So let's call this M and V. All right, we know it depends on X. All right, so all right, so we have V times X, right? V times this distance X, and then you have plus M, because I drew M as going counterclockwise, and then you have this distributed load, which is causing a moment. So it's minus the integral from 0 to x of Wx times W naught over L x dx, right? It's x times W of x. So we got 1, 2, 3, 4. 1, 2, 3, 4. Okay, so we got all the terms. All right. So we know what V is right now. It's just this term right over here. So we can stick this into V, and we can solve for M. This is what we're after, the moment at the cut. Okay. So the moment is equal to the integral. Let's just evaluate the integral. Actually, let me just move it over first. It's from 0 to x, W naught over L x squared dx, and then move this to the right. So what's V? So plus this term, it's minus W naught x squared over 2L plus W naught L over 2 multiplied by x, right? I just moved this term over, I moved this term over, and now I want to move this term over. So you have minus W naught L squared over 3. Right? So you guys could evaluate the integral and simplify this. So you get W naught x cubed over 3 divided by L plus, well, it's actually a minus W naught x cubed over 2L, right? I'm multiplying the x throughout. So you have plus W naught L x over 2, and then you have this last term, minus W naught L over 3. Okay. Any questions so far? So you have two terms over here that could reduce, right? This is W naught x cubed, W naught x cubed. This is 2L. So you have this fraction, you can simplify it, and you can't simplify this term. So let me just give you the simplified version of the moment. Where is it? I did a little trick too. After I simplified this part, I made it one complete fraction on the bottom. I just multiplied these two terms. I multiplied this by 3L and 3L on top, so I multiplied it by 1. And I multiplied this one over here, 2L on top and bottom. So I could make it easier when I integrated using this equation. Okay, so I'm just going to give you the final product of it. Alright, so the moment you get is equal to minus W naught. You could do the algebra and figure this out. You get x cubed minus 3L squared x plus 2L cubed. Alright, so when you simplify this is it completely simplified. Okay? So this is n. right? So now we want to find the elastic curve. So we have to use the second order differential equation to find it, right? And EI is constant because this is a uniform beam. So I isn't changing with X. It's just a constant beam, and the Young's modulus is constant. Okay. So let's take this into the differential equation and let's solve it. Let's integrate twice, and then we can get the elastic curve. All right, so we have d squared y over dx squared. I'm going to move EI to the other side because it's a constant, so we can just move it to the other side. And this is equal to m, okay? M of x, I called it over there, I'm just going to call it m. So let me just erase this and call it m. Okay. So we know m is equal to minus w naught over 6L multiplied by x cubed minus 3L squared x plus 2L cubed. Is it 2? Okay. All right. So this is just a differential equation. It's the second order. Do you guys know how to integrate it? You just separate the variables, but it's already separated, so you could just integrate. All right. So let's integrate once. You guys just tell me what it is. Right? If you integrate this, the order is going to go down 1. Okay? So what do you guys have? This is just a constant. So you have minus W naught over 6L multiplied by what?
X to the 4th over 4.
Yeah. X to the 4th over 4 minus 3L squared x squared over 2 plus 2L cubed x plus what?
C1.
Plus, yeah, a constant, C1, okay? And we're going to need boundary conditions to evaluate these constants. So let's integrate it another time. So now you have y of x. So this is equal to minus W naught over 6L multiplied by x to the 5th over 20 minus, what is this, 3L squared x cubed over 6 plus 2L cubed x squared over 2 plus C1x plus C2. Right? You're integrating again, so you're introducing another concept of integration. So, all right, so this is our elastic curve. This is what they're asking for. So what is this telling you? This is telling you how this beam is going to bend. So this beam is going to look like this. Right? From this distributed load, it's going to look like this. Remember, this was the x-axis. This was the y-axis. So it's going to look something like this. That's what this curve is telling you. And obviously it's negative, so you would expect that, right? The slope would be negative of the highest term, which would say it's going downwards, right? If it was positive, it would be going this way. That would mean the load was pointing upwards. You guys follow? That's pretty simple to understand. Okay. Alright, so let's erase this. Alright, so now we need the boundary conditions. What are the boundary conditions?
Y of 0 is 0.
Huh?
Y of 0 is 0.
Yeah, exactly. Y of 0 is equal to 0 over here, that's right. Right? Because there's no deflection there. So y of 0 is equal to 0. That's your first condition. What else?
Y prime of 0 is also 0.
Yeah, exactly. Yeah, the slope over here is 0. So dy dx over here is 0. Remember I drew the picture, it looked like this, the beam? So the slope over here is 0. The slope here is 0. So that means dy dx at 0 is equal to 0. Or you could just say y prime of 0 is equal to 0, like he said. Yeah, that's fine. It's the same way of expressing it. Okay. So you have dy dx of 0 is equal to 0. So that's the second condition. Is there anything else? Or no? No, there's nothing else. Okay. All right, so we have these two conditions, and we have two unknowns, right? So we want to solve for these constants of integration. But you'll notice if you plug in 1, what do you get?
0.
You get
For
C
C1.
sub 2 is 0. What happens when you plug in this boundary condition? We already have it differentiated over here, the line above it. So if you plug in 0 over here and 0 for x,
C1
you get
0.
C1 is equal to 0. So this one will give you C2 is equal to 0. This one will give you C1 is equal to 0. Okay, so that worked out really nice because sometimes the algebra is nasty when you solve for these, depending on your boundary conditions. All right, so you got the constants of integration. They're just 0. So our elastic curve for part A, we just solved for it. So for part A, the solution, we want to solve for y of x. Now we could bring the EI over there. We can move it to the other side. So we have y of x is equal to minus w naught over 6. Sorry if it's squeaking. 6LEI. Oh, it's almost my last name. It's close. This needs NER. All right. So we have this term, and it's multiplied by this. All right. So it's x to the 5th over 20 minus this. You could reduce this. That's just 1/2. So it's minus L squared x cubed over 2, and then you have this reduces to 1. So you have plus L cubed x squared. Okay, so that's your solution for part A. So they want the elastic curve. This is the equation. All right. So in part B, what do they ask you again for part B?
Maximum deflection.
Oh, okay. Yeah, they want the maximum deflection. All right, so we have the elastic curve. If we want the maximum deflection, where is the deflection going to be max?
At B.
At B, yeah, x equals L, right? Because I just drew the picture before, it looked like this, right? So the max deflection is going to be over here. All right, so that's this distance over here. We want to know what that distance is. That's the max deflection, right? And it's going to be negative because it's below the y-axis. So let's plug in. So we want to know at what at x equals L, what does y equal? All right. So we want to know this term right here. So all we have to do is plug in L for x. So you have minus W naught over 6 LEI multiplied by L to the 5th over 20 minus
L to the 5th.
Yeah, they're all L to the 5th. They better be all L to the 5th. Because if they're not all L to the 5th, that's how you can check yourself when you're doing the exam. They should all be the same power. Okay? So this is L to the 5th, L to the 5th, L to the 5th, right? So this is L to the 5th over 2, because I'm just plugging in L here, and this is also L to the 5th plus L to the 5th, right? So you could reduce this, and it comes out to, all right, so y of L equals, it's 11 over 120 W naught L to the 4th over E I. Okay, so after you reduce this, it comes out to negative 11 over 120 W naught L to the 4th over EI. So that's your maximum deflection, this part B. And then for part C, they want to know the slope at the free end, right?
Yeah. So we just want to derive y of x.
Yeah, the slope at the free end. What?
We want to just plug in L for EI dy dx.
Yeah, because you want the slope. Yeah, exactly. From over here, you could use this differentiated version, or you could differentiate this, but you're going to get this. Yeah, so you look at this equation again, right? We found out c sub 1 is 0, so now we want to plug in L for x over here, and you can get dy dx at x equals L, what the value is. Okay? So let's do that. So what I was saying is you could go ahead and differentiate this again, but you're just going to get this. So there's no point. And this constant we found out was 0. So I'll just leave that out. So we want to find for part C the slope at the free end. So we're looking for dy dx at x equals L. So we're looking for this, right? So this is equal to minus W naught over 6LEI multiplied by L to the 4th over 4 minus 3L to the 4th over 2 plus 2L to the 4th. So the deflection at the the slope at the free end, dy dx at x equals L is equal to you get minus W naught L cubed over 8EI. Okay. That's the slope at the free